Hello and welcome friends. In our previous lecture, we have seen least cost branch and bound. Today, we'll use least cost branch and bound to solve an optimization problem which is known as the traveling salesman problem. So what is this traveling salesman problem? Think of a salesman who wants to sell some goods in different cities and he wants to visit these different cities. Now, let's suppose while he is moving from one city to another, he incurs some cost. So some cost is associated from while he travels from one city to another. And the idea is that he finishes his tour by visiting each of these cities, and he should end his tour at the city from where he started. And while moving from one city to another, there is some cost that is incurred. And his objective is to visit each of these cities by starting from some city A and ending his tour at the same city, and the total cost that he incurs by visiting each of these cities should be minimized. So that is the objective, as you can see on the slide. So the objective of this salesman is to minimize his total cost incurred while visiting each of these cities. So as an example, as you can see on the slide, let's suppose there are 4 cities. We have labeled them U, V, X and W, and this graph there represents the paths between each of these cities, and the label for each edge between these 2 cities represents the cost that is incurred to the traveling salesman. Now the objective of the salesman is to visit each of these cities U, V, X and W such that the total cost incurred by visiting these cities is the minimum. He aims to reduce the total cost, and he has to visit each of these cities, and he has to end his tour at the same city from where he started. So as you can see on the slide, this path here represents the least cost path for this particular example, and the total cost for this path is, or this tour to be more precise, is 7. As you can see, the salesman starts from U, visits W, then he visits V, and then he visits X, and finally he ends his tour at the same vertex from where he started. So this is the simple objective of this traveling salesman problem, that we have to identify the minimum cost tour. Now, in order to formulate the least cost branch and bound solution to this traveling salesman problem, let's consider this traveling salesman problem is given to us in the form of a directed graph, okay, where we have this set, as you can see on the slide. We have a set of vertices representing cities and a set of directed edges E representing the cost incurred from moving from the source city to the destination city. So we can represent our traveling salesman problem in the form of a directed weighted graph with the V vertices and E is the set of edges. And let's suppose the total number of cities that we have, that is the size of this vertex V, is equal to n. So n is the number of cities. And we can also represent the same traveling salesman problem in the form of a matrix A, I, J, which has n number of rows and n number of columns, wherein a cell A of I, J represents the cost of edge from source I to source J. So we can represent our traveling salesman problem in the form of an adjacency or a cost matrix, to be more precise, where each cell in the matrix A of I, J is the cost of the edge from source I to destination J. And let's suppose in the actual graph there is not an edge between source I and destination J vertex, then in that case the cell for that particular edge I, J will be equal to infinity. So A of I, J will be equal to infinity if I, J, that is the edge I, J, does not belong to the set of the edges. So this is the basic formulation from which we'll be trying to build our least cost branch and bound solution. Now, in order to generalize things, we'll assume that a tour for this traveling salesman problem always starts from vertex 1. Now we can have labels assigned to the vertices in our traveling salesman problem differently, but when we want to build a least cost branch and bound solution to this particular problem, we'll assume that this traveling salesman always starts from vertex 1 and ends at the same vertex, because he has to make a tour of all the cities. So he starts from vertex 1, goes to all other cities and finally ends at vertex 1. Now you can take any particular vertex and label it as vertex number 1 from where you want to start the tour, or from where the traveling salesman wants to start the tour, and the remaining vertices can be labeled accordingly 2, 3, 4 and up to n. So this is a general assumption. This will not kind of make any particular problem to us if we assume that a traveling salesman always starts and ends his tour at vertex 1. Now in this case, the solution space, as you can see on the slide, can be given by a set S. Now what will this set S contain? It will contain permutations with the starting value equal to 1 and the ending value equal to 1. As you can see here, it will contain sequences starting with 1 and ending at 1. As I said, we'll be considering this general case that a traveling salesman starts his tour from vertex 1 and ends his tour at the same particular vertex. So our solution space will contain sequences of vertices starting at 1 and ending at 1, and in between there will be the permutations of the remaining vertices, that is 2, 3, 4 up to n. So this pi here represents a permutation of 2, 3, 4 and so on up to n. So starting vertex is 1, ending vertex is 1, and in between there are permutations of 2, 3, 4 and n, each of these particular vertices. For a complete graph, it is obvious that the size of the solution space in that case would be n minus 1 factorial. However, most of the times these graphs may be sparse, or there might not be edges from one particular node to another or from one city to another. So we can further reduce the size of the solution space. For a sparse graph, the size of S can be further reduced, as you can see on the slide, by restricting S so that it has this particular property. Now what does this property say? So our solution starts from vertex 1 and ends at vertex 1, and these are the intermediate nodes or vertices in our solution. Now we'll say that this sequence belongs to the solution or is one of the solutions if and only if the intermediate vertex pair, the consecutive intermediate vertex pair I of j comma I of j plus 1 belong to E. So what this basically means is that these intermediate pairs of vertices will exist in our solution. So for example, I of 1 and I of 2, similarly I of 2 and I of 3, similarly I of 3 and I of 4 and so on so forth. In general, we'll say I of j comma I of j plus 1. So these are the two vertices which are consecutively appearing in our solution. So this pair of intermediate vertices will only exist in our solution if and only if there is an edge between this particular node I of j and I of j plus 1 in the graph. So if there does not exist an edge between I of j and I of j plus 1 in the actual graph, then that particular pair of consecutive nodes cannot appear in a solution. So that way will obviously reduce the solution space from n minus 1 factorial if we have a sparse graph. Now this holds for j greater than or equal to 0 to n minus 1, and for this particular solution I of 0 will be equal to I of 1, which is equal to 1. So our solution basically starts from vertex 1 and ends at vertex 1, and each pair of consecutive nodes in between starting and ending node appears in a solution only if there is an edge between those pair of, or a directed edge from node I of j and I of j plus 1, as I have already said. Now for the sake of an example, if we consider this particular complete graph here, we have not assigned any edge weights to this graph for the time being in order to make things simple. So this is a graph. So a solution space tree or a state space tree for this particular graph will look something like this. So what this basically means is we start from vertex 1. So this vertex 1 here is the node from where the traveling salesman person will start his tour and also end the particular tour. So starting from this node number 1, we consider this as the root. Okay, so node number 1 is implicitly considered. Okay, so we are at node number 1. So which other nodes can we visit from this particular node number 1 or vertex number 1? So we can go to vertex number 2, we can go to vertex number 3, we can go to vertex number 4, as you can see on the slide. So there are 3 possibilities, as we have only 4 vertices in this example. So if we start from vertex 1, we can go to vertex number 2, we can go to vertex number 3, we can go to vertex number 4. Similarly, starting from vertex number 1, if we have then moved to vertex number 2, okay, then we can go to vertex number 3 and vertex number 4. We cannot go back to vertex number 1 because we have not yet visited all the other vertices. Okay, so we implicitly consider that we have started from vertex number 1, so we can go to vertex number 2, then we can go to vertex number 3, then we can go to vertex number 4, and finally After we have visited vertex number 4, it means we have traveled to all the cities. Vertex number 1 has already been visited. We visit 2, 3, 4, and then we go back to vertex number 1. So that move from vertex number 4 to vertex number 1 will not be shown in the tree. As I said, that our tour will start and end at vertex 1. So we have to find the intermediate sequence. So we take vertex number 2, take vertex number 3, then go to vertex number 4, and finally end in vertex 1. Similarly, an alternative path would be we start from vertex number 1, go to vertex number 3, go to vertex number 2, then to 4, and then again end at vertex number 1. Similarly, another alternative path would be we start at vertex number 1, go to vertex number 2, then we go to vertex number 4, then we go to vertex number 3, and finally end again at vertex number 1. Similarly, these are the other possible paths. These leaf nodes here represent solutions to our problem. All these leaf nodes here represent the solution. What this means is that a path from the root to this leaf node represents that pi, as I earlier said in that slide. So we have started at vertex number 1, go to 2, go to 3, go to 4, and end at 1 again. Similarly, we have started at vertex number 1, go to 2, go to 4, go to 3, and vertex number 1 as well. So this is just an illustration how the state space tree would look like for this particular example in this case. Now, as I said, we are trying to build a least cross branch and bound solution to the traveling salesman problem. And if you remember, in the previous lecture, we used certain functions to build a least cross branch and bound solution. As you can see on the slide, we need 3 functions. One is the cost function, which helps us to identify the final solution node. Similarly, we need a ranking function, CCAP, which helps us select the best node from the currently active nodes to expand our solution. So we have a set of active nodes, we choose the best feasible node from active nodes and build our solution so that we quickly reach that particular solution node. And the final one is the upper bound function, which helps us to bound intermediate nodes or to restrict growing other particular solutions. So these are the 3 functions that we'll have to define in order to build a solution, a least cross branch and bound solution to the traveling salesman problem. So the first one is the cost function. So how do we define the cost function for this least cost branch and bound solution to the traveling salesman problem? So for a leaf node in the state space tree, the cost of that particular node S would be the length of the tour defined by the path from root to S. So if you look at the earlier example, this particular tree here, so what will be the cost of node 11? As I said earlier, we have not assigned weights to the edges in this particular tree, but it is obvious the cost at node number 11 would be the sum of edge 1 to 2 plus cost of edge 2 to 3 plus cost of edge 3 to 4 and finally plus the cost of 4 to 1. I hope made it clear earlier that we start and end our tour at vertex number 1. So this leaf node here means we have to consider this path of this tree. So the total cost would be 1 to 2 plus the cost of 1 to 2 going from vertex 1 to 2 plus the cost of going from vertex 2 to 3 plus the cost of vertex 3 to 4 plus the cost going from vertex 4 to 1. So this will be the sum of these individual edge costs. So for the cost function, we have mentioned for a leaf node S, the length of the tour defined by path from root to S. Similarly, if S is not a leaf, then it would be the cost of a minimum cost leaf in the subtree of S. We'll see in a moment what this basically means. Let's look at this tree as an example. So this node number 12 here is a leaf node. What will be the cost of node number 12? As you can see from the tree, we have implicitly started at vertex number 1. So what is the cost of going from vertex number 1 to vertex number 2? We'll have to consider that. We also have to consider the cost of going from vertex number 2 to vertex number 4. Okay, we keep on adding these costs. Similarly, we'll add the cost of going from vertex number 4 to vertex number 3. And finally, since we have to end the tour at vertex number 1, we'll also add the cost of going from vertex number 3 to vertex number 1. So this will be the total cost if this node is a leaf node. In this case, node number 12 is a leaf node. Now, in case the node is not a leaf node, so let's suppose on the slide we'll consider node number 3 here. So what will be the cost of node number 3? As you can see from the definition, for a node which is not a leaf node, the cost of that node is cost of the minimum cost leaf in the subtree of S. Now let's have a look at the subtree of this node 3. How many leaves are there? There are 2 leaves. One is 13, another one is 14. So the cost of this node 3 would be the cost of the minimum cost leaf. So we'll have to calculate cost for node number 13 and cost of node number 14. Whichever is minimum will be assigned as the cost for node number 3. We'll later see how we compute these costs in more detail. So we define the cost function. Now we also need a ranking function, CCAP, which we have used to build the least cost branch and bound solutions. Now for the traveling salesman problem, we use a reduced cost matrix for defining the approximate cost or the lower bound for finding a least cost branch and bound solution, or we also represent as CCAP. So for the traveling salesman problem, the ranking function CCAP of a particular node can be obtained by using a reduced cost matrix. So we'll have to see what a reduced cost matrix basically is. So let's define that. Initially, we'll talk about individual rows and columns. A row or a column in any given matrix is said to be reduced if it contains at least one zero and all remaining entries are non-negative. What does this basically mean? Let's take an example. This is a matrix here, and let's suppose this is a cost matrix of traveling salesman problem. So since we have 5 rows and 5 columns, it means we have the total number of vertices is 5. And let's also look at what each row represents. This row here represents, this is label it as row number 1, this is row number 2, this is row number 3, this is row number 4, this is row number 5. Similarly, this is column number 1, column number 2, this is column number 3, this is column number 4, and this is column number 5. So what does this row number 1 represent? It means this is the cost of going from vertex 1 to vertex 1. Column 1 represents vertex 1, this row 1 also represents vertex 1. So this cell here, A of 1 comma 1, represents the cost of going from row number to column number. So row number is 1, column number is 1. Similarly, this value here represents the cost of going from row number 1 to column number 2, or vertex number 1 to vertex number 2. Similarly, this 30 represents the cost of going from vertex number 1 to vertex number 3. Similarly, this 10 here represents the cost of going from vertex 1 to vertex 4. Similarly, vertex 1 to vertex 5. So each row basically represents the total costs for node number 1. Similarly, if we look at the last row here, it represents node number 5. Okay, so this value means going from node number 5 to node number 1. This 4 here means going from node number 5 to node number 2. Similarly, node number 5 to node number 3, and so on and so forth. In the same way, if we look at a column, so what does this column basically represent? As I said, this is labeled as 1, this is labeled as 2, this is labeled as 3, similarly so on. So this column represents moving to vertex number 1. So make it clear in a moment. This is 4 and this is 5. So this value here means moving from vertex number 1 to vertex number 1. Similarly, this 15 here means moving from node number 2 to node number 1. Similarly, this 3 here means the cost of moving from node number 3 or vertex number 3 to vertex number 1. So all these values in this particular column correspond to the costs associated with going to node number 1. Similarly, if we look at this particular column, it represents the costs for going to node number 3 from all other particular nodes. So as I said, a row or a column is reduced if it contains at least one zero and all other remaining values are positive or non-negative. So let's look at this column. We look at this column. Does it contain any zero? It does not contain any zero. So how can we introduce a zero in this particular column? The simplest thing is we take the smallest value from this column. So in this case it is 4, and subtract it from each of the values in this particular column. So this is the result. We have selected 4, the minimum value from this particular column, and subtracted it from all other values in the same column. So this becomes 16, infinity remains the same, 5 minus 4 is 1, 6 minus 4 is 2, and 4 minus 4 is 0. Now what have we done? We have reduced the cost of, as I said, this would be vertex 1, vertex 2, vertex 3, vertex 4. Earlier I said each column represents cost of going to that particular column, or if this is for example column number 2, it means cost of going to node number 2. This column represents costs associated with going to node number 3. Similarly, a row represents costs of moving away from a particular node. So if this is for example node number 1, this is node number 2, this is node number 3. So row number 2 represents the costs associated with going out from node number 2. So this is the cost of going to node number 1 from 2, this is the cost of going to node number 2 from 2, this is the cost of going to node number 3 from 2, so we are moving away from node number 2. So each row, the number associated with that row represents the costs associated with going away from that node, and the column represents the costs associated with going to that particular node represented by that column. So we have reduced this row in the sense that we have reduced the cost of going to particular column. So in this case, we have selected as column number 2 and we have subtracted the minimum value. Since there was no 0, so we have subtracted the minimum value from each of the values in the particular column, and that way we have reduced the cost of going to vertex number 2. Since this is column number 2, so we have reduced the cost of going to vertex number 2. So if we look at the problem, that is the traveling salesman problem, our objective is to find the minimum cost store. Since we have to visit in the solution, we have to visit each node exactly once. So if we look at this column, that is column number 2, we can come to vertex number 2 from any other vertex. Okay, and we have subtracted a small value from all the values from this particular column. So any tour would simply be minimized or reduced by that small amount that we just subtracted. So a minimum cost tour will still remain a minimum cost tour because we have simply subtracted a value from all possibilities that go to node number 2, as you can see on the slide. Okay, and we have subtracted a small amount from all values from the column. It means a minimum cost tour will remain a minimum cost tour even after this subtraction operation. As I said, we are simply reducing or removing an amount from a particular column. A column represents the costs associated with moving to a particular vertex. So if we select any particular tour, all tours will have that value, that amount that we just subtracted, reduced. So a minimum cost tour will still remain a minimum cost tour. It will not affect our final solution. Similarly, if we want to reduce a row, in the example you can see we have selected row number 3, means we are considering weights which are associated with moving away from vertex number 3. There is no 0 in this particular row, as you can see on the slide. The smallest value in the row is 2. So we select this 2 and subtract it from all the values in that particular row. So this is the final row that we get. We have introduced a 0, so it's a reduced row now. Okay, and again this subtraction operation will not affect the final result, that is a minimum cost tour will still remain a minimum cost tour even after this subtraction operation. What we have done, as I said earlier, is that a row simply represents the costs associated with moving away from a particular node. In this case, in the example, it is node number 3. So we have subtracted a small amount, an equal amount from all possibilities, all weights. So as I said, a minimum cost tour will still remain a minimum cost tour even after this subtraction operation. This is how we reduce a particular row or we reduce a particular column. We simply introduce a 0 if there is not a 0 already in the row or the column. How do we do that? We select a minimum value from the row or the column and subtract it from all values in that particular row and column. So again, as you can see on the slide, we have mentioned that subtracting a constant t from every entry in one column or one row of the cost matrix reduces the length of every tour by exactly t. Tour which is minimum will still remain the minimum even after this subtraction operation. That is what we have mentioned on the slide. A minimum cost tour remains a minimum cost tour following this subtraction operation. So we have seen how we reduce a row or a column. Overall, we can say a matrix has been reduced if and only if every row and column is reduced. What that means is every row and every column must include at least one 0 and all other values have to be non-negative. Now, after, let's suppose we are given a starting cost matrix and we want to reduce this. So we'll apply this row reduction and column reduction repeated depending upon our requirement, so that the complete matrix is reduced, so that every row and every column has a 0 included. And we'll keep a record of the amount that we subtracted from the rows and the columns. So we sum that up, all the values that we subtracted from the rows and columns in order to get a reduced matrix. We'll sum that up, and we can use that value as the C cap for the root of the state space tree. So we'll remember, given a cost matrix, initial cost matrix, we will reduce that cost matrix and remember the total amount that we subtracted to achieve a reduced cost matrix. And that particular value we can use as the C cap value, as the lower bound value for the root of the state space tree. So this is only for the root, how we estimate the C cap value for the root. What about the intermediate nodes? Let A be a reduced cost matrix for a node R in the state space tree. So let's suppose we have a reduced cost matrix associated with a particular node, and let S be a child of that particular node, such that the tree edge R, S corresponds to including edge I, j in the tour. So we are building our state space tree, trying to find our solution, and we are at node number R, and we have to expand and we have to find its children. And let's suppose the first child that we generate is S. So S is the first child that we are currently expanding for node number R. And let this S be such an edge which corresponds to including the edge I, j in the tour. This I, j is from the traveling salesman graph. So this edge R, S is for the state space tree. And while we are building our solution, or we are trying to find our solution in the state space tree, we, let's suppose, want to expand this particular node R by trying to build its child S. And while we are building this child S, it basically means we are trying to include edge I, j in the tour. Okay. So in that case, if this S is not the leaf, how do we identify whether the node S that we just generated in the state space tree is not the leaf? By keeping the track of which particular nodes we have already traversed. If there are no remaining nodes after this particular node S, it is obvious that it is a leaf node. However, if all the vertices, we started from 1 and we have n nodes, 2, 3, 4, 5, 6, 7 up to n have all been visited by considering this vertex S, then S will be a leaf node. So let's consider this case. If S is not a leaf, so there are still some vertices which are yet to be visited, then the reduced cost matrix for S may be obtained as follows. So for non-leaf nodes, we obtain the reduced cost matrix something like this. So what do we do? Change all entries row I and column j of the current cost matrix to infinity. As I said, while we are trying to build this child S, let's suppose it corresponds to including the edge I, j in our tour, vertex I to vertex j. This edge is being considered. So what do we do? How do we obtain the reduced cost matrix for this? We change all the values in row number I and all the values in column number j of this current cost matrix to infinity. Now what does this do? This prevents the use of any more edges leaving vertex I or entering vertex j. Since we have to visit each vertex exactly once, this is how we try to prevent that. Okay, this is how we enforce that each vertex is visited exactly once. So we are including an edge I, j in our tour. Then in the current cost matrix, we'll simply change all the entries in row number I and column number j to infinity. Okay. Similarly, we'll set A of j, 1, the current cost matrix that we just modified. We included infinity for row I and column j. On the same matrix, we change the value A of j, 1 to infinity. What is j? J is the destination node for the edge I, j that we are currently trying to include in our tour. And j, 1 here means finishing the tour. Okay. So if S is not a leaf node, it means we are not yet finished with all the nodes, then we cannot end the tour. So we are including edge I to j in our tour, but after we have visited j, we cannot directly go to 1 because there are still certain nodes to be visited. So in order to ensure that we do not terminate our tour after we visit vertex number j, we change the value of A of j, 1 to infinity. So this prevents the use of edge j, 1 as it will end the tour. Again, we are currently dealing with the case where S is not the leaf node while we are searching the state space tree. Now, after we have done these two steps, we further reduce all rows and columns which are not all values equal to infinity. So that is what has been mentioned in step number 3. We reduce all rows and columns in the resulting matrix except for rows and columns containing only infinity. This will be more clear in the example that will be working out in a couple of moments. So this case we are considering for S, where S is not a leaf node. Now, as I earlier said, that we will have to remember the total amount that we removed from a matrix while we are reducing it. Okay, while we were reducing its rows and columns, we will have to remember that amount, and let's suppose that R is that total amount which has been subtracted from step number 3. Then C cap for this particular node S, we are currently expanding the children of R, and the first child that we considered was S. Okay, this is just a general assumption. So the least cost or the lower bound for this node S would be whatever was the C cap value for its parent R plus the value that has been stored at A of I comma j plus this R. Now this R, as I said, will be obtained from step number 3. So for each node, while we are trying to build our solution in the state space tree, we'll associate a C cap value with each child that we generate. And how do we obtain that? We'll use these 3 steps to obtain a reduced cost matrix, and from that reduced cost matrix we'll remember the total amount R that was subtracted in order to obtain that reduced cost matrix, and we'll use that value to get our lower bound for a node S using this particular equation as has been shown on the slide. However, for leaf nodes, the C cap value will be equal to the actual cost, and it is easily computed as each leaf defines a unique tour. So as soon as we reach a leaf node, as I earlier said, how do we identify that we have reached a leaf node? Is that we have visited all the vertices. We just need to end our tour by visiting back vertex number 1. Okay, so that is what we'll be remembering, or that's what we'll be doing. So for leaf nodes, the C cap value will be equal to the actual cost that we need, and it is easily computed for each leaf, and each leaf will obviously represent a unique tour, and we'll select the tour which has the minimum cost, or we'll select that particular leaf which has the least cost associated with it. Okay, after we have built or searched the state space tree. So we are done explaining the 2 functions that we'll be using to build our least cost branch and bound solution to our traveling salesman problem. The cost function, we have already defined how we will be using this cost function. The ranking function has also been illustrated how we'll use or construct a reduced cost matrix associated with each child that we are expanding currently for the currently active node, and how we'll use it to compute the C cap values. And finally, we also need an upper bound function. Now, for the sake of simplicity, we will use the upper bound of a node R to be equal to infinity for all nodes. R here is an intermediate node. Okay, so for all intermediate nodes, we will assume that the upper bound is equal to infinity. But as soon as we reach a leaf node, we will use that particular value, that C cap value, for upper. As I said, that for a leaf node, the cost is equal to the C cap value, the approximate cost, and as soon as we reach a leaf node, we will save that particular value as upper. Okay, for the remaining intermediate nodes, we'll use upper as infinity. It will be more clear in a moment as we'll illustrate that. So let's work all these steps around and look at an example, a practical example, how we compute the reduced cost matrix, how we identify the final solution, or the least cost branch and bound solution to the traveling salesman problem. Now on the slide, as you can see, we are given a cost matrix with the 5 cross 5 cost matrix. It means we have a total of 5 nodes, okay, and each of these values represents the cost of going from one vertex to another vertex. As I earlier illustrated, for example, this one is row number 2 and column number 1, so it means the cost of going from vertex 2 to vertex 1, and similarly the other values as well. Again, we build on our basic assumption that we start from vertex number 1, and let's assume that we are at vertex number 1 and we have to make choices for the next vertex in our tour. So we start at the root, assume that we have already selected vertex number 1, that is the start of our tour, and we build or generate the children for this particular route. For this route, the current cost is equal to 0. For the time being, we will set this cost equal to 0, set the upper value equal to infinity, okay, and we have to estimate the lower bound for this particular route. And how do we do that? If you remember in the earlier slide, I said that the amount that we remove from the first cost matrix, the given cost matrix, after we reduce it, okay, can be used as the C cap value here. So that is what we will be doing. We will try to reduce this current cost matrix in order to obtain the C cap value for the route. So let us look at the steps. Now we select the first row for reduction. Now if we look at the first row here, there is no 0. No 0 exists in the first row, so this row has not been reduced. So we will select the minimum value from this row, which is 10. So we select this value and subtract this value from all the values in this particular row. So what do we get? This is the reduced row that we get. This will be 0, this will be 1, 20, 10, and this will remain in infinity. And we remember the amount that we just removed in R. Okay. Now if we look at the second row also has not been reduced. Okay. So how do we reduce it? We select the smallest value from this row, that is 2, and subtract it from all other values in this particular row. So we subtract 2 from all the values in this particular row, and this is what we get. However, the amount that we just subtracted will be added to the earlier values that we removed. So R will be equal to 10, which was for the first row, plus 2, which was removed for the second row. Similarly, the third, fourth, and the fifth rows are reduced by removing 2 from the third row, 3 from the fourth row, and 4 from the fifth row. We keep on adding them to the R value. Now we also have to reduce this matrix column wise. This is just row wise that we reduced the cost matrix. We will also have to see if the matrix can further be reduced column wise. Now let us consider the first column in the current matrix. If you look at this column, there is no 0 in this column, okay, then the smallest value is 1. So we remove this 1, okay, and add it to the earlier values that we just removed. So column number 1 has also been reduced. Now let us have a look at column number 2. It already contains a 0, so no need for reduction for this particular column. However, column number 3 does not contain a 0, so the smallest value is 3. We subtract it from all the values and we get a reduced column, and we also add this 3 to the earlier values that we just removed. So we keep on summing them up. Column number 4 and column number 5 have already contained a 0, so there is no need for reduction. So the total amount that we just removed from the starting cost matrix was equal to 25. And from now onwards, we will use this reduced cost matrix for our further processing, and we will use this 25 as the value for C cap. That is what we have done here. So now we will be using the reduced cost matrix, and C cap is the equal to 25 for the root node, the amount that we just removed from the cost matrix. Now the children for the root node, as I said earlier, that we started from vertex number 1. Which other vertices can we visit? So we can visit, for example, 1 has already been visited, so we cannot visit 1 again. 2 can be visited, 3 can be visited, 4 can be visited, and 5 can be visited. So let us generate all these children. So as you can see on the slide, we have generated node 3, 4, 5, and 6. So let us suppose this is R, okay, this is S, and generating this child basically corresponds to adding the edge 1. This root here represents vertex 1 that we have considered vertex number 1, and considering this child S means we are including edge 1 to 2 in our tour. Similarly, node number 3 represents that we are including edge 1 to 3 in our tour. Similarly, node number 4 represents that we are including edge 1 to 4 in our tour. Similarly, this node number 5 represents we are incorporating edge 1 to 5 in our tour. Okay. For the time being, let us consider this first case, node number 2 here. So this is R, okay, this is S, this is the child that we are building, and the edge that we are currently incorporating is 1 to 2. Okay, so this is the edge that we are currently trying to incorporate in our tour. So we'll have to obtain C cap value for this vertex number 2. How do we do that? We'll have to reduce the matrix for node number 2. Okay. So the matrix associated with R is this one for the time being, and for S we'll have to obtain a new cost matrix. So this is the matrix that we'll be trying to reduce, and as I said earlier, the first thing that we need to do is that we need to consider the edge. We are considering 1 to 2. So row number 1, which is this one, and column number 2, which is this one, will all be set to infinity. So that is what we just did. So for node number 2 corresponds to incorporating edge 1 to 2 in our tour. So row number 1 and column number 2 will have all values set to infinity. That is what we just did. This is infinity and this is infinity. Also, the step number 2 that you should remember is that A of j comma 1 will be also set to infinity. So j in our case is 2. Okay. So A of 2 comma 1 should be equal to infinity. That is what we will just do. So this is 2 comma 1 has been set to infinity. And now the third step involves reducing this matrix. So we'll have to look at each of the rows and columns. Okay. Let's look at the first row. It contains all infinities, so no need to reduce this row. Row number 2 includes a 0, row number 3 also includes a 0, row number 4 includes a 0, and row number 5 also includes a 0. What about columns? Column number 1 includes a 0, column number 2 is all infinities, so no need to reduce. Column number 3 includes a 0, 4 includes a 0, and 5 includes a 0. So R in this case would be equal to 0. How do we obtain C cap for node number 2? It is simple. C cap for 2 is equal to C cap for 1, that is this one. Okay, R was this, S is this. If you remember, C cap of S is equal to C cap of R plus this R plus A of this should be 2 comma 1. That is in our case it is 2 comma 1. So what is this? C cap of R, it is equal to 25. C cap of 1 is equal to 25, which we have already computed. R is equal to 0, and A1 of 1 comma 2 is equal to 10. Now this A1 of 1 comma 2, as I earlier said, that has to be considered from the matrix associated with R. So in our case, the R is node number 1, and this is the matrix which is associated with R. Okay. So this is A1 of 1 comma 2, which is equal to 10. So this value will be added here. So the total value that we compute for C cap of 2 is equal to 35. So we'll save this value for C cap of 2, and similarly values can be calculated for node number 3, node number 4, and node number 5. So this is A2 for node number 2, this is A4 for node number 4, this is A3 for node number 3, and this is A5 for node number 5. Now you can see that for A5 we had to reduce row number 4 because it did not contain. We set row number 1 and column number 5 equal to infinity, and then this from this matrix you can see that since this was set to infinity, no value here was equal to 0. No value here was equal to 0, and we had to reduce this by removing 3 from each value here. Okay. So this is how we computed C cap for node number 2, how we computed C cap for 3, 4, and 5. Now we remember these nodes and the costs associated with them, C cap values associated with them. Now all these 4 nodes are active. Node number 2 is active, 3 is active, 4 is active, and 5 is active as well. Least cost branch and bound selects that particular node from among the active nodes which has the least cost associated with it. So if you can look at these values, the best node or the node which has the least cost from among the active nodes, the node with the least cost is node number 4, and that is the node that we will be selecting for expansion. So we'll generate its children. We have visited vertex 1, then we visited vertex number 4, and from 4 we can go to 2, 3, and 5. So these are the 3 children that we can generate for node number 4. Again we have to compute C cap values for all these nodes. Okay, and This is how we did that. These are the reduced cost matrices for each of these nodes. You have to remember that in order to generate these reduced cost matrices, we will have to use the cost matrix associated with node number 4, okay, not the cost matrix which was associated with node number 1. And that is what we have shown here. A of 4 is the cost matrix that we obtained for node number 4. And for generating the reduced cost matrix, or for computing CCAP values for node number 6, 7 and 8, we will have to use the reduced cost matrix for node number 4. And from this matrix we computed these reduced cost matrix for node number 6, 7 and 8. And similarly we computed the CCAP values as was shown in the earlier slide. Again, at this level we have nodes 2, 3, 5, 6, 7 and 8 as active nodes. Here node number 2, 3, 5, 6, 7 and 8 are all active nodes, and least cost branch and bound selects that particular node which has the least cost associated with it. And as you can see, this node number 6 has the least cost from among the active nodes, and we'll use this node to expand and try to find our solution. That is what we just did. We generated node number 9 and node number 10 and also computed the CCAP values associated with them, and these are the reduced cost matrices associated with node number 9 and node number 10. Again, we have generated these reduced cost matrices from A of 6, that is this particular node, okay, not from 4 or not from 1. I hope you remember that if this is R and this is S earlier for the first case, and then this is R and this is S for the second matrix. So we'll have, in order to generate the reduced cost matrix for these two nodes, we'll have to use the reduced cost matrix for node number 6. That is what we are remembering here. And now at each of these stages, these are still intermediate nodes. We have not generated a leaf node yet. We have not reached a leaf node yet, and for all these cases we are setting upper equal to infinity. Okay. Now at this stage node number 2 is active, 3 is active, 5 is active, 7 is active, 8 is active, 9 is active and 10 is active. Least cost branch and bound selects that particular node which has the least cost associated with it, and it is obvious that node number 10 is the one with the least cost currently. So we'll use this and expand this particular node. Now at this stage the only child that we can generate for this node is node number 11, which associates with including vertex number 3 into this tour. So we started from vertex number 1 and we moved to vertex number 4. From 4 we used the edge 4 to 2, then we used from 2 the edge from 2 to 5, and then we used the edge from 5 to 3. All intermediate nodes have been visited and there is no other vertex left that we can visit. So it is obvious that we have reached a leaf node. Okay. So the reduced cost matrix associated with A11 has been computed something like this, and it is obvious that we generated it from A of 10, that is this particular matrix here. Okay. And the cost that we computed was 28. Okay. So since this is the leaf node, it will be the CCAP value here will be equal to the cost, actual cost associated with this particular node. So what this means is we also save, since we have reached the leaf node, we also save this value to the upper. Earlier we used upper value equal to infinity for all the intermediate nodes. As soon as we find a leaf node, we set our upper equal to the CCAP value that we compute for that particular leaf node. So we have reached a leaf node, and that is one of the possible solutions. However, we are not yet finished because there are still certain nodes which are active. Okay. It simply means that we are not finished yet, so we'll have to traverse them as well. So among the active nodes, node number 5 has the least cost. However, the least cost associated with node number 5 is greater than the upper value that we just computed. So we'll simply bound this node. We will not further try to kind of expand the solution for this particular node. Now among the remaining nodes, node number 2 is the one with the least cost, but again the cost here is way greater than the upper value. So again we'll discard this node. From among the remaining nodes, node number 8 is then considered. Again its value is greater than the upper value, so again this is discarded. Similarly node number 7 is discarded. Similarly node number 9 is discarded, and then node number 3 is discarded as well. And there is no remaining active node left, and we have found a single leaf node with a cost amount equal to 28, and this is the minimum cost amount that we have found for the traveling salesman problem. And this leaf node corresponds to the least cost path from 1 to 4, as you can see this path here. This is the path that we have to follow. So 1 and 1, the start and ending vertex is implicit, that is vertex number 1. So we from 1 we go to 4, then we go to 2, then we go to 5, then we go to 3, and then we go to 1, and the total possible cost for this traveling salesman problem is 28. So this was the illustration of how you can use least cost branch and bound to solve the TS traveling salesman problem. Now the upper bound function in this case is straightforward. There is no code to be written for it. Just have to choose it as infinity for the intermediate nodes. As soon as you find a leaf node, then you'll use that value as the upper bound. It is possible that there might be more than one possible least cost paths. Similarly, the only thing that you need to implement in this case is, it is similar to the problem that we discussed in the last lecture, that is the least cost branch and bound formulation that we talked about in the earlier lecture. It is similar to that. The only difference here is that we have to write algorithm for reducing the cost matrix, and that is an assignment to you. I've given algorithms and code snippets for all other algorithms that we have discussed so far, be it branch and bound for other problems, be it backtracking and others. So I've given the algorithms for all the other problems that I have discussed. For this problem, this is just an assignment to you. You can build or construct an algorithm which you will use to reduce the cost matrices at each intermediate node, and which will help you to find a solution to the traveling salesman problem. So with this, I'll finish my lecture today, and I hope that you have got a good understanding of how least cost branch and bound can be used to solve the optimization problem that we discussed, that is the traveling salesman problem. And I hope that you'll work out a good algorithm for implementing the reduction of the matrices, and you will use it to write a complete algorithm for the traveling salesman problem using least cost branch and bound. With this, we have finished discussing branch and bound, and I wish you good luck for the remaining lectures.